All right, welcome you guys. This is our last section in chapter 2, and it's just going to be the algebra of functions. Okay. So the main thing that's tough about this section is really just the notation. Notation's kind of strange looking and it really throws people off. Okay, so let's look at this first page in detail. So on the right-hand side of each one of these equations, you're going to see the long way of writing these operations on functions, and probably the proper way to think about them, right? On the left-hand side of each one of these equations, you're going to see the shorthand way of writing them. And this is just, utter, not laziness, but, so we can do math with speed, right? When in this situation here on the left, I don't have to write X twice. Okay, so it can become cumbersome if you're doing math over and over to have to write the X twice. And so this is another way of thinking. Just take the function f and the function g and add them together. So they won't write the x 2 times, you guys. Okay, same thing over here. This means take the function f and subtract g from it. Okay, there's no multiplication going on here. I know it sure looks like multiplication, but it's really just this meaning over here on the right-hand side where it's subtract the 2 functions. It's just our shorthand way of writing it. Same thing here. Okay, this really just means take the function f and multiply it by the function g. And so now we don't have to write the x 2 times, we just write the x 1 time. And then if I want to do f divided by g, we'll write it this way. So what I'll do is I'll take the shorthand notation and I'll always write the long one out just for the notes so that the understanding is there, okay? All right, so up at the top, they're giving us 3 different functions, the function f, the function g, and the function h. And it says to evaluate if possible. Okay. So remember that it's always f of x. And so whatever you see inside the parentheses, that's always going to be plugged in for x, okay? So this part over here is just telling me which function, because I got 3 of them now, so it's really important that I know which one. So we're going to be using this function f up here. So we are going to substitute a -3 in for every single x. So x squared, so -3 squared, minus 3 times -3 plus 1. So we took every x up here at the top and we just replaced it with a -3. And then we just got to do the math. So -3 times -3 is 9. And -3 times -3 is positive 9. When we add this all together, we get 19. So that's going to be our answer for f of -3. All right, number 2, g of 4. So again, remember that 4 is going to be substituted in for x, but now we're going to be doing it in the function g. So I'm going to go up here to my function g, and where I see the x, I'm going to put a 4. Eight minus 4 is 4, and the square root of 4 is 2. Yeah, this one's kind of weird, but we definitely do things like this a lot, so it's not a rarity. We're going to be substituting a plus 1 in for the x. Remember, whatever's inside the parentheses has to go in for x. So we're going to go up to the function f. So we're going to be looking over here. And everywhere where we see an x, we're going to put an a plus 1. So x squared would mean a plus 1 squared minus 3 times a plus 1. Okay, so we've got to take a plus 1 and multiply it by itself. And then we'll go ahead and distribute the -3 into the parentheses. So we got -3a minus 3. And we'll bring the plus 1 along. And now, of course, we're going to be doing our foiling or distributing. All right, so we got a times a, which is going to be a squared, a times 1, 1 times a, and 1 times 1. And then we'll bring along the minus 3a, and I might as well combine these 2 things while I'm here. So -3 plus 1 would be -2. Okay, so now we'll just combine all the like terms. I only see an a squared, but I'm going to have to combine a another a, and a negative 3a. So I'm going to combine all those together. A plus a is 2a. 2a take away 3a is going to be negative a. And then I'm going to combine all of the constants. So this plus 1 and this minus 2 will make a minus 1. Now I get some students who like all of a sudden put an equal 0 in there. They're like, let me put an equal 0 and let me use the quadratic. If there is no equal 0 from the start, then you can't just go and insert one. And it turns out we're actually done. So it breaks my heart when students continue on and I have to mark them off a little bit for not understanding what the directions mean. Okay, it doesn't say solve up here. We're just plugging a plus 1 into the function and cleaning it up. Okay, we're not solving. So we're done. All right, g of 10. So I think you guys get the gist. We're going to be substituting 10 in for the x, right, on g. And here's g. So we're going to substitute a 10 into that. So we got the square root of 8 take away 10. And this ends up giving us a negative, okay? And so this is actually going to be, gosh, what would we write? Not in the domain, I guess would be a good answer because this ends up being imaginary, right? So let me write down, this is imaginary. So there's no real solution. Oops. Okay, and so probably the best answer would be to say that 10 is not in the domain. 10 is not in the domain. We'll talk more about this, or what that means, but let me just give you a little preview of how to think about this. The graph of this function, if you were to go, online and graph it, well, we actually technically know, okay? If we were to take the square root of 8 minus x and rewrite it as negative x plus 8, and then factor out the negative, we know that this would shift to the right 8 spaces because this lies to us, right? So it's going to be right 8 spaces. So let's pretend this is 8 right here. Normally a square root graph goes like this, right? But ours is going to go the other way because remember that this negative made it reflect across a vertical axis. So pretend that this is my vertical axis or the y-axis, whatever. It was going this way, but now we reflected it and it's going the other way. So why is it important that we look at the graph here? Well, think about what it means for me to evaluate when x is 10. X equals 10 is right here. And you can clearly see that's not even on our graph, right? It's empty right there. So when we say not in the domain, that's exactly what we mean. We mean there's going to be some sort of discontinuity or emptiness in the graph there, okay? And that it doesn't make sense to plug 10 in because when we plug 10 in, we won't get any real value out. All right, moving on to new stuff now. So this isn't just us substituting in, this is us now doing algebra on the functions, okay? So remember what this means. This is the first page I talked about. This is the shorthand way of writing f of negative 8 minus g of negative 8. Okay, so you have to know that that's what that means. That's going to be something that you're going to have to know. And now it just becomes exactly what we have been doing. You're going to have to substitute negative 8 in for the x in the function f. So we're going to come up here and we're going to put negative 8 everywhere that we see an x. So negative 8 squared minus 3 times negative 8 plus 1. Okay. And maybe it would just be better to find these separately. You know what? I'm going to do that just to make sure that we don't get confused. So I'm going to do this work off to the side, you guys. And actually, I'm going to erase it because I want to do it colored. So let's see here. Let's go with blue for this. So to find f of negative 8, we know we have to substitute in negative 8 into the function f. All right, negative 8 times negative 8 is 64. Negative times a negative is a positive. 3 times 8 is 24. If we add this all up, it looks like we're going to get 89. So 89 is the first part for f of -8. Now let's go in here and let's get a g of -8. So we're going to take -8 and we're going to substitute it into the function g. So we have the square root of 8 minus -8. So that's going to become 8 plus 8. Ooh, I like that number. Because 16 is a perfect square, it gets us 4. Okay, so now we're going to do 89 minus 4. So 85. Oops, black. There we go. Okay. Number 6, same functions. I'm going to write out what this means using the longer way instead of the shorthand notation. It means plug in 0 into g, plug in 0 into h, and multiply the two. Okay, so let's go ahead and get g of 0. So we're going to substitute 0 into the function g. So it's going to be 8 minus 0, which is square root of 8. If we break down the square root of 8, that is going to be 4 times 2, you guys. So it looks like it's just going to be 2 root 2. You'll have to use the broken down versions for Connect Math, you guys. All right, so I'm going to go ahead and put 2 root 2 here. And now let's go and get h of 0. So h of 0 means plug 0 into the function h. That's the first time we've used h. So 2 over 0 plus 1 would just be 2 over 1. And 2 divided by 1 is 2. So this is going to multiply by 2. Now remember, when multiplying, it's only these two numbers that multiply by each other. So 2 times 2 is going to get us 4. And the root 2, just kind of bring it along. Okay. And then finally, h of -1. So we're going to substitute -1 in for the x. So we've got 2 over -1 plus 1, which gets us 2 divided by 0. Remember, division by 0 is not allowed in mathematics, right? So this is undefined. And again, what we could say is just like on the last one, not in our domain. It turns out that the graph of this, which we're going to graph a bunch of these in chapter 3 or 4, I can't remember, at -1, there is going to be a big gaping hole. There's a vertical asymptote at -1. Pretend that's -1, you guys. And so it's not part of our domain. There is no value for that input. So not in our domain. Oops, I put no in our domain. Not in our domain. Okay. All right. So now the only difference is, we have 3 functions again, is they're just not giving us numbers this time. They're leaving them as x's instead of like putting -8 there or something like that. So let's start by writing down the longhand notation. So this is r of x minus t of x. And this one over here would be r of x divided by t of x. For me, it's really helpful to do this rewrite, because then I just see it as substitution. It's like, okay, r of x. Well, what is r of x? You go up here, it says r of x is x squared plus 3. So I'm going to put an x squared plus 3 in its spot. Now, it's very important that you use parentheses when you are substituting in, especially the second function, because now we're subtracting away t of x, which is x plus 4. I need parentheses or else I will have the wrong sign on the 4, because you can see that we're going to have x squared plus 3, but when I distribute that negative, it's going to change that plus 4 to a minus 4, you guys. So it's so incredibly important that you remember to put those parentheses. All right, I'm going to put the squared term first, the linear term or the x to the first term second, and I'm going to combine like terms to put my constant last. So we have -1 here. Oh my. Sometimes this board glitches in the craziest ways. It's like after I write it, it'll change the font color. Oh my, it's doing it still. Okay, let's see if it comes back. Let's see if that works. There we go. Now remember, don't go solving it, right? This is done, you guys. Don't put an equal 0 if there never was an equal 0. Just leave it alone. The directions do not say so. Okay. All right, let's move on to number 9. So r of x, we'll substitute x squared plus 3 in, since that's r of x. And then we'll substitute t of x in. Now the directions have changed a little bit. It says write the domain in interval notation. Okay, so this one's done, but now we just have to write the domains for both of these. So here's the moral of the story, you guys, at least for right now. If there are no radicals or no fractions, then the domain will always be all reals. If there are no fractions or radicals, the domain will be all real numbers, or negative infinity, right, to positive infinity. If it's interval notation, okay. Let's see. There we go. Okay. So if we're looking at this first one, right, there's no fractions, there's no radicals. So the domain's going to be negative infinity to infinity. Okay. Now, the second one does have a fraction, huh? So let's talk about what to do if there are fractions or radicals. Okay. What to do if there are fractions. For fractions, set the bottom denominator equal to 0, solve. That is what x cannot be. Remember, the bottom of a fraction cannot be 0. So when you set it equal to 0 and you find out what makes it 0, that is what x cannot be. All right, for radicals, set the stuff underneath the radical, the radicand in other words, right? I'll put that in so I'm more legit here, right? Set the radicand. Set the stuff, you know what, let me do a better place to put that's right here. Greater than or equal to 0. That is what x can be. Okay, so let's talk about that. We already talked about the first one, but the second one. Remember, if you have a radical, this stuff has to be greater than or equal to 0. 0 is okay. We can square root 0. The square root of 0 is 0. We can square root positives, right? Even if it's not something pretty like the square root of 2, it still at least has a value, okay? So we want to make sure that that stuff is greater than or equal to 0. That's what x can be. You don't want to have negatives in there because then you start dipping into imaginary numbers. And we're looking at functions on the real number plane on the xy axes, right? All right, so for fractions, you set the stuff in the denominator equal to 0 and you solve. So we're going to take x plus 4 and we're going to set it equal to 0. And that is what x cannot be. So how do I show in interval notation my domain? So -4 is not allowed, but everything this way is and everything that way is. So for our domain in interval notation, we're going to describe each one of those pieces with a union between. So for this piece on the left, it's going to be from negative infinity all the way to -4. And remember to use a parentheses because -4 is not allowed. It's not included. If you put a square bracket on it, you're including it. For the other piece, it'll be from -4 all the way to positive infinity. You'll always see these parentheses on the number that is not allowed with like a union between them. Sometimes we'll have multiple numbers removed, okay? So you'll always have a union and parentheses on that number. So that's going to be our answer to what is the domain. Now, do you have to do it if you can just see it? We've done so many things on restrictions that if you're like, X can't be -4, I know from the section on restrictions, then just go right away to this graph. You don't have to do all this solving for me. That's in case you get a tricky one where it's not like self-evident what the what's going to make it 0. All right. So let's write out the longhand here. So this is going to be S of X multiplying by T of X. So if we substitute S of X in, and then we substitute T of X in, we have to put a 1 underneath to multiply fractions, and we will multiply straight across. So we get 2 times X plus 4 over X times 1, so X. And you could distribute, you cannot distribute. I think both are perfectly fine, you guys, so I'll box that. Now you should be able to quickly tell me what X can't be, right? You can't have zeros in the denominator, so X cannot be 0. So on a number line, 0's been removed, but every other number to the right and to the left is okay. So if we were going to describe our domain using interval notation, we'd say from -infinity all the way to 0. And then from 0 all the way to infinity would be our domain. Okay. Now this is kind of tough. This is actually the beginnings of calculus, you guys. Calculus is all, at least Calc 1 is all about derivatives, and this is part of the definition of the derivative. Okay. All right, so this expression right here we're going to be working with, and this has a name, it's called the difference quotient. We would read that f of x plus h minus f of x over h, okay? And for now, let's just use it. If you end up, it basically is just slope, you guys. That's all it is finding the slope between 2 points. Let's get used to using it because sometimes the computation of it can be a little bit difficult, okay? So I believe Connect Math asks it this way, where it does it in 2 parts, because really the hardest part, if you go back to the difference quotient, is this part right here. That is where most students kind of fall apart if there's a spot. Okay, so let's go ahead and do that. So it says find of f of x plus h. Now remember, we did a problem a while back that's very similar to this, okay? If we go back to like the very beginning and we look here on this page, right? This one over here says f of a plus 1. And it was kind of strange, but anything that's inside of the parentheses is x. So we had to plug an a plus 1 in everywhere where we saw an x up here on f of x. Well, we're going to do that same exact thing here, okay? So you've kind of already done this. So we're going to take x plus h and we're going to substitute it in for the x, okay? So we're going to go over here to our function, and where I see an x, I'm going to substitute in an x plus h, okay? I'll do it in red so we know that's what we substituted in. You're going to clean it up, right? You're going to do all the math to it you can. You're going to make it nice and neat. All like terms combined, etc. Okay, so that is what f of x plus h is. I'm going to box it. So the reason they're having you do that is because now if I want to find f of x plus h minus f of x over h, we've already done about half of that, right? This first part is f of x plus h. Well, we found it. So let's go ahead and write it down. And then minus parentheses. Remember I told you this parentheses are important. Minus f of x. So you're going to take f of x and you're going to substitute that in there. All over h. You're just going to go ahead and distribute the negative. Now, if you do all of your math right, at least at this level, all of the h in the denominator should cancel. So if you find that your h in the denominator is not canceling, then you have made a mathematical error somewhere. Okay, so just a little tip, because I have some students who will, go put it in. If your h didn't cancel, guys, don't put it in. Maybe you forgot the parentheses or you did some other math incorrectly. All right, so you can see that we're left with 5h over h. And so indeed, the h's do cancel, and we just get 5 left over when all is said and done. And that is indeed the slope of that line. This is what this is finding, is it is finding the slope. Okay, let's do another one. A little tougher. We're going to up the difficulty a little bit. Okay, so we got to find f of x plus h. Remember, that means you're going to take x plus h and you're going to plug it in for all of your x's up here. Okay, so I'm going to go ahead and get this guy ready. So it's going to be something squared minus 3 times that something plus h. Okay, so we're going to substitute x plus h in all these blanks. And then we're just going to do a bunch of math and clean it up. This one's a little tougher than the last one as far as the math. We got to do x plus h times another x plus h. And I'll go ahead and distribute this -3. And we'll FOIL out this binomial. And this is all letters, so it gets funky when it's all letters. Let's see, x times x is x squared. And typically we go alphabetically when we're multiplying letters by each other, you guys. So even though it looks like x times h, I'm going to write it as h times x. And then the next one would be h times x also. And then h times h is h squared. Okay. Only thing that I see being able to combine is the hx plus another hx will get us 2 hx's. I don't see anything else being able to combine. In other words, I don't see any other like terms. So that's your answer for what is f of x plus h. Now we're ready to go to our difference quotient. Let me write the formula down to ground myself. That's it. Those of you who are going on to calculus, right? Memorized. Okay, f of x plus h. That's the first thing it says, right? We got it. That's what we found in part 1. So let me copy that piece down. That is a big one. Minus parentheses, right? Don't forget those parentheses. I can't underestimate how important they are. All over h. We do things right. We know that our h's should cancel, our h in the denominator, right? I'm distributing the negative now, you guys. Now let's see what stuff can cancel. X squared minus x squared. Negative 3x, positive 3x. Positive 8, negative 8. So I think that what we have left is 2hx plus h squared is 3h all over h. So every single term in the numerator that's left over has an h in it. That means we can factor an h out of all of them since each one of them has at least one to contribute. So here's what is left if we take an h out. And what do you know? I'm feeling pretty good. The h's are supposed to cancel, and they did. So this would be our difference quotient. This would be the slope at any given point on this curve. Okay, ugly x. I think I made it worse. Oh yeah, not getting any better here, you guys. Hold on. When my pen gets low on batteries, it starts making choppy lines. There we go. I never knew there was I'm sure there's so many batteries I don't know about, but this one requires a quadruple A. And it's so bizarre. I can't even find it in stores. I have to order it online. So sometimes it's a little low for a while because I have to go order it from Amazon. Okay, so that is our difference quotient. Okay, you guys are doing calculus. Okay, so this one was really tough for me personally. I don't know why. I just, at the time, it just flew over my head. Okay. So this open circle is different than like the dot that we saw earlier, right? If I write this f dot g, that means to multiply the two functions. But this open circle means something different. It means one of the functions is going to get substituted into the other function. It's called function composition. So this is read as f composed g. All it means is that the function on the right is going to get plugged into the function on the left. Know when to make that one word plugged into the function on the left. So this open circle just means one function will get substituted into the other function. And we can write that two ways. This open circle will mean it, or we can write it this way where literally g is inside of the function f. It's inside the parentheses for the function f, right? If I look at these two parentheses right here, right? G has been substituted inside of them. So that means G will be inside of F. Okay, and I always draw this arrow to help people realize the one on the right gets plugged into the one on the left. Okay. So we're going to be substituting G into F. So we're going to take this and we're going to substitute it in anywhere where we see an X. So we will have x squared minus 3 times x plus 1. We're going to put 5x plus 4 in to the blanks, and we'll just do all the math. Again, we're not solving, we're just evaluating, so don't add an equals 0 or anything and bust out your quadratic formula, you guys. Just clean it up. All right, so we're going to go ahead and distribute this -3 inside of that. So negative 15x minus 12. And then we'll FOIL out this guy. So we get 25x squared. 5x times 4 is 20x. 4 times 5, still 20x. 4 times 4. You know, we might as well do it while we're here. Negative 12 plus 1 will be negative 11. And then let's just combine some like terms. 20x, 20x, and 15x all need to get combined. So 20 plus 20 is 40. 40 take away 15 is 25. So this is going to be 25x. And then we'll combine the 16 and the 11 together. So positive 16 take away 11 is going to be 5. Box it, you're done. Okay, now they like to ask it the other way around. So we go back and steal. Is this attached? Let's see if it's attached. Let's see here. Sorry, this normally allows me. Okay. Just have to cruise back and forth. But this time it means that F is getting substituted into G. So let me just write these functions down. Okay, I think it was what? X squared minus 3x plus 1. And then G of X was 5x plus 4. Okay, so we're going to take F we're going to substitute it into G. So we're going this way with it now. All of this is going to get substituted in right there. So here's what we have. We have 5 times x plus 4, but x is going to be x squared minus 3x plus 1. This one's a lot easier than the last one. So we'll just distribute, combine like terms, done. So we get 5x squared minus 15x plus 5 plus 4. 5x squared minus 15x plus 9 would be our final answer for G compose f of x. Okay. So who is getting plugged into who? Okay. Well, the one on the right always gets plugged into the one on the left. So we're taking G and we are substituting it into F. So we're going to take this and we're going to place it right there. Okay, so we've got 5. Oh, sorry, I meant to be in black here. So we've got 5 parentheses something squared, take away 1. And we know that that something is going to be the square root of 5x plus 5. Remember, square rooting and squaring are inverse operations, so they will undo each other. So we end up with 5 times the quantity 5x plus 5. Distribute, combine like terms, and you're done, you guys. So we get 25x plus 25, take away 1. So we get 25x plus 24. Okay, it's probably going to ask us the other way. Yes. So now F is going to get substituted in to G. So we're going to take F, and we're going to plug it in right there. So I'm going to write down G, the square root of 5 times something plus 5. Okay, 5x plus 5. And we're going to substitute in 5x squared, take away 1 there. Okay. So distribute. 5 times 5 is 25. 5 times 1. Okay, these are going to cancel with each other. So we get the square root of 25x squared. And this one's kind of weird because I get this as an answer and I see why students would put that. But technically you have to have absolute value brackets around the variable, because anytime you square root something, you should get a positive number out. Like if you go to your calculator and you put the square root of 9 in, your calculator is going to say 3. It's not going to say -3. It's going to report out the principal root, okay, the positive root. And so while this may seem like this is a positive quantity, it's not necessarily. What if x is negative? If x is negative, like let's say it's -2, then we do end up with a negative number. And it's impossible for us to square root and end up with a negative number out, right? So you've got to remember to put those absolute value brackets on it, or you will miss it, you guys. And that's just to ensure that what you get out is positive, okay? Let me put a little comment here. We need absolute value brackets around the variable to ensure that it's positive. We need absolute value brackets around the variable. 5's already positive, so you don't have to put it around the 5. That'd be like redundant, right? We need absolute value brackets around the variable to ensure that it is positive. That's the tricky part to that problem. Okay, F compose. So for these, there's a lot of ways to do it, you guys. And I'm just going to show you what I think is the easiest. We're so used to this start on the right and move to the left. So what I'm going to do is I'm going to substitute 9 into G, get some number, and then substitute that number into F. We're going to work from the right all the way to the left, okay? So we're going to start by putting 9 into G, okay? So let's figure out what G is with 9 inside of it. So I'm going to take the 2x plus 8, sorry, the 2x minus 8, and I'm going to substitute a 9 in. So I end up with 2 times 9 is 18. 18 minus 8 is 10. Then I'm going to go ahead and go to F now, and I'm going to substitute 10 into it. Okay, so it's going to be 3 over, and I'm going to put the 10 where the x was, you guys, in this function up here. Okay, so 3 over 10 minus 4, so 3 over 6, which if you divide them both by 3, that gets you 1/2, right? So the final answer is going to be that last one. It's going to be 1/2. This is the final answer, okay? So you don't plug 9 into both. You plug 9 into G. Whatever you get from that, you plug into F, okay? All right, let's try this again. So 6 is going to get plugged into F. Whatever we get from that, we're going to substitute into G. All right, so let's start off by taking F and plugging 6 into it. All right, so we got 3 over 6, take away 4, so 3/2. So now we're going to take that and we're going to substitute that into G. So 2 times 3/2 minus 8. Let's put the 3/2 in there. All right, we're going to just cancel these 2's, cross cancel. So we're just left with 3 minus 8, which is -5. So that's going to be your answer, okay? Given F and G, find F compose G and the domain of F compose G. Okay. All right, you guys. So for function composition like this, you want to, let's go ahead and figure out who's getting plugged into who, okay? So it's the one on the right that gets plugged into the left. So we're taking G and we're going to substitute it into F. Okay, so we're going to go ahead and take F, and instead of writing the X, we're going to put 3x minus 2 in its spot. Maybe I'll do that in a different color. All right, so 3x plus 2, and then don't forget the plus 2, or sorry, minus 2. And then don't forget the plus 2 that was already there. Okay, so we're going to go ahead and cancel out the minus 2 and plus 2. So we're left with 3 over 3x. We'll go ahead and cancel the 3's. And that does not leave me with x, you guys. That's my number one wrong answer. Remember that x is in the bottom, so it can't magically creep up to the top. It still has to be in the bottom. So there is a 1 in the numerator left over. Think about it, 3 divided by 3 is 1, right? So it makes sense that there's a 1 there. Okay, now for the domain for function composition, you have to check 2 things, okay? So let's just write this down and make this explicit. For the domain of function composition, number 1, find the domain of the inner function, or the function on the right, of the inner function on the right. And then number 2, find the domain of the answer of the composition. Find the domain of the composition, aka your final answer. The domain will be the intersection. The domain will be the intersection of the 2. Okay, so the inner function in our case is G. That's the one that got plugged in. That's the one on the right, okay? So our inner function, this is going to be like part 1. So if we find the domain of G, there's no fractions, there's no radicals. So the domain would be -infinity to infinity, like we talked about a few slides ago, right? Since there's no functions, there's no fractions or radicals, the domain is -infinity to infinity, and I'm just going to handwrite that in. Okay. Now let's go and get the final answer. composition, right? And that's 1 over x, right? So f compose g of x, we found out it was 1 over x. The domain of this is that x cannot be 0, right? Because the denominator can never be 0 for a fraction. So that would mean negative infinity all the way to 0, union 0 to infinity, right? Exclude 0. Okay, now I'm going to take the intersection. In other words, you know, not the intersection. Gosh, what's a better way to word that? I guess the more exclusive of the two, the one that has stricter restrictions. And then I'm going to use that as my answer. Okay, no, that would be the intersection. Yeah, that is an okay way to write it. Okay, so that would be my answer. This one's saying negative infinity to infinity. This one has some restrictions. I'm going to go with the one that has the restrictions. Okay. Now, why do we have to consider both? Sometimes when we do the math, we lose the domain of the inner function, but I have to make sure that I think about the domain of the inner function. And I think this next example, maybe not, but a good example to show us would be, what if we had gone the other way around? What if we had g with f inside and the value that we were plugging in was -2, right? Okay. Well, think about it. The first thing we would have to do is we would have to plug -2 into f. Well, what happens when we plug -2 into f? If we do 3 over -2 plus 2, we get 3 over 0, which isn't even a number. That's undefined. Now I have nothing left to plug into g, right? So we really have to check that innermost function, that one on the right first. Whatever its domain is important, because when I plug a value in there, if I can't plug it into this one, then I'll have nothing to plug into the other one. So that's why we can't just look at the final answer and accept it. We do have to make sure that the function on the right that we have checked its domain also. So hopefully that made some kind of sense, you guys, okay? All right. Given blah, 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 find two functions such that, blah, blah, blah. Okay, I think there's what, a couple of these. Let me see how many. Okay. So I'll just kind of briefly go through this. This is getting you ready for the chain rule in calculus. That's the intent here with this one. And so it says, given h of x, find two functions f and g such that h of x equal to f compose g of x, so that h of x is equal to f compose g of x, okay? All right, so there's a lot of different answers. Let me give you a few so you can understand what I mean by there's a lot. Okay. So one possible answer could be this. Okay, so let's check it. Now remember, when I write it this way at the top of the screen, this means G is getting plugged into F. So if I plug G into F, right? If I take G and I plug it in here, look what I get. So h of x, I am saying, can be found by doing f compose g of x. And that would mean plug in to the square root function 3x minus 7. And it worked. It got us the original, right, you guys? It's not the only such function. Let me give you some other possible answers. This could work. Okay. If I were to do, if I'm saying h of x is f compose g of x, so g gets plugged in to f, I'm going to take it and I'm going to substitute it in for the x. And if I do that, you can see that we get the square root of 3x minus 7. Okay. And then there's kind of the chintzy, you know, like, well, no, duh, this one's not very interesting, but it would work on all of them, is just making f of x the function itself. And then just making g of x x. Because in that case, if I'm going to find f compose g of x, I would just take this and I'd plug it in for X, and it would just get you get F back again, right? If I plug X in for X, then nothing changes, okay? So there's infinitely many correct answers to this, you guys. Probably the one that we were hoping that you would spot is the first one. But honestly, to answer the question, any one of those would work. It's a good enough one. So I want to find two functions, f and g, such that, again, when I plug g into f, I get h of x. Oops. So probably a good one would be x cubed plus 8. And then let g be x plus 1. This is the one we're hoping that you would spot for calculus, at least. So if you take x plus 1 and you plug it in right there, right? Then what we're saying is that f composed g of x should get us h. Let's see if it does. Yeah, if I just put x plus 1 in for x, you guys, then I end up with this, which is the original. It matches, right? And lots of different answers again, but I'm hoping that this is the one that you will see. Okay. All right. So we're going to get all these values now, not in an algebraic way, but straight up from a graph. So I'm going to write these down the longhand, right? Remember, this is shorthand for f of -3 minus g of -3. This one is shorthand for g of -2. Oops, let me write that higher, you guys. G of -2 being divided by f of -2. Okay, these other ones are a little bit different. We'll do this in a second. Okay, so I have to find f of -3. Now remember, this is the x value, right? The -3 is the x value, you guys. You've always got to keep that in mind, that whatever's inside the parentheses is x. All right, so if x is -3, that would be right here. That's where x is -3. F is the blue function. So if I look at the blue function, I can see that that is at 0. So I'm going to write down 0. If I look at the red function, which is g, and that's not at 0, that's at -1, -2, -3, -4. It's going to be at -4, you guys. Right here is the y value of -4. So I'm going to write down -4. So that's going to get me 0 minus -4, aka 0 plus 4. So the answer should be 4. So I'm giving you x values. You just got to find the y values. That's it. So let's go over here to g of -2. Remember that -2 is the x value. So here is -2. Let me erase all the marks from the previous one. Here's where -2 is. And I'm going to go to the function g, so the red function. So down 1, 2, 3, 4. So -4 would be the y value. All right, now I'm going to go to the blue function and go up to 1, 2. Okay, so the y value would be 2 for that one. -4 divided by -2. I'm sorry, -4 divided by 2 is -2. All right, so you're only going to spit out y values, you guys, for the given x value. All right, for these, it's function composition. So we know that we plug in and then plug in again, okay? So this is the x value though, -1 is the x value. So I'm going to go to where 1 is, and I got to find the y value on f. So I got to find the y value on the blue. So up 1, 2. So it looks like the y value is going to be 2, you guys. Okay, and I'll write this one out a different way to kind of help a little bit. So the other way of writing function composition is like this. It's g with f inside of it. Okay, it's another way to write function composition. We talked about that on the first slide. What we just did is we just did this part. We said, hey, when x is 1, what's the y value on f? And we said that that was 2. So that is going to be what we're going to have inside of the parentheses. We're going to have a 2 in there. Okay, should probably do it in blue, I guess. Okay, so now that's going to be my x value. That's going to be my x value. But I'm going to go to g this time. So when x is 2, here's 2, I got to go to the red function. So 1, 2, 3, 4. 4 would be my answer to that. Okay. So let's do another one because we got to get good at this. So this is f of g of -3. So we're going to get g of -3 first. So we're going to go to where x is -3. 1, 2, 3. And we're going to have to say, okay, what is the y value on g? G is the red curve. So from that -3, I have to go down 1, 2, 3, 4. So -4 would be the y value. So I'm going to put down a -4 for the inside of the parentheses. Okay, so now x is -4, you guys. This is my new x. 1, 2, 3, there's -4. Okay, I'm gonna have to find the y value, but on f this time. F is the blue one. So we went down 1, 2. So it's going to be -2 for the y value. And this one's kind of funky. We haven't done one yet where we've taken f and composed f with itself. But let's go ahead and get the inside. We got to find f of -3. So we're going to go to where -3 is. 1, 2, 3. And f is the blue curve. Well, that would be 0. So that's going to be our inner number is 0. So now we're going to go to where 0 is. 0 is right here. And I got to look at the f curve, which is the blue curve. So from there, I'd go up 1, 2. So +2 would be the answer. Okay. So you start off with a certain x value, but then it changes, right? Once you find what the y value is, that y value becomes the new x value. Okay, for the outermost function. All right. Let's do this word problem. That's our last one. Okay. A party balloon is being filled with helium. As the balloon is filling, the radius of the balloon is changing at a rate of 3 inches per second. So you start off with your balloon, right? Its radius is 0 at time 1, or at time 0, sorry. Then you start to blow it up, and it says it's changing 3 inches per second. So at a second later, we would expect our balloon, to have, pretend it's spherical, a radius of 3 because it grew 3 inches. Then a second later, it's changed another 3 inches. So now it should be 6 inches for our radius, etc., etc. Okay, so it starts off at 0, it's 3, it's 6, it's 9, it's 12, okay. Write a function that represents the radius of the balloon after t seconds. Okay, well, it's changing 3 inches every second, 3 inches per second. So 3t or 3x, whatever variable you want to put there, right? Okay. And this works because what happens when you plug a 0 in? 3 times 0 gets you 0. That matches. When you substitute a 1 in, 3 times 1 gets you 3. That matches. 3 times 2 gets you 6. That matches. So it's working. Whatever you put down, you always want to check it. Okay. All right. Write a function that expresses the volume of the balloon as a function of its radius r. So you would just have to Google this. You'd have to Google the volume of a sphere because that's what this balloon is shaped as. Okay. So if you don't have it memorized, Google volume of sphere. Okay. All right. And it turns out that the volume of a sphere is 4/3 pi r cubed. Just Google that. Done. Okay. All right. It says evaluate V compose R of T and interpret the meaning in the context of this problem. So we know that R is going to get plugged in to V. So that means we're going to take this function and we are going to substitute it in for the R. Okay. So let's do that. So we are going to have that V compose R of T is 4/3 thirds pi, and in the place of r cubed, we're going to put 3t in there. Okay, and then we'll do the math. So we get 4 thirds pi, and then we have to do 3t times 3t times 3t. All right. So we get 4 over 3 pi. 3 times 3 times 3, you guys, is 27. And t times t times t is t cubed. So we're going to go ahead and divide this 3 into this 27, making it 9. And we will multiply straight across. I'll put an over 1 here, so it's really clear, you guys, that we're multiplying straight across, okay? So 4 times pi times 9, let's just do the 4 times the 9. What is that, 36? And then the pi and the t cubed, right, are all in the top. In the bottom, we just have 1 times 1, which is 1. So I'm not writing that, okay? So there you go. All right, so it says interpret the meaning in the context of this problem. Well, this would be the velocity as the function of time instead of as a function of radius. If you look up here on part B, this is our velocity as a function of r. So if somebody gives you a radius, you're able to find the volume. Why am I saying velocity? I think because I have calculus on the mind, you guys, excuse me, volume, right? So this is the volume as a function of the radius. What we found now is the volume as a function of time, okay? This is the volume function of time. So what's the difference here? And why do we like this? Why is this even important, okay? If I said to you, what's the volume at 2 seconds? Let's do volume at 3 seconds. If I didn't have this handy dandy equation, I'd have to do more work. What I'd have to do, because my volume is only given as a function of the radius, and I can't plug time into that, right? I can only plug radii into that. So what I'd have to do is I'd have to go up to this function and I'd have to plug the 3 in there. So 3 times 3 gets me 9. Okay, so the radius is 9 at 3 seconds. Now that I know that the radius is 9 at t equals 3, now I can finally use this formula. Now I would put the 9 in there. Okay, so I would get 4 over 3 pi times 9 cubed. And I'm just going to have my calculator. Well, what would that be? 729. So it'd be 4 thirds pi times 729. Let me see what 4 times 729 is. Okay, so I actually just 3 goes into that. So I'm actually going to cross cancel, you guys. 3 goes into 729. 729 divided by 3. 243 times. And now I'll do the 4 times the 243. So if I do 4 times 243, I'm getting 972 pi, okay? That took a lot of work. I couldn't just take the fact that time was 3 and plug it into the volume equation. I had to take the fact that time was 3, plug it into the radius equation to get the radius, and then I could finally plug that into the volume. But if you look at what we've created here, I have the volume as a function of time. So we have a shortcut. Instead of going through all that madness, now I really can just take the 3 and plug it in. I can take the time and plug it in. So if we put 3 in for the t, right? We know that 3 times 3 times 3 is 27. So 36 times 27, what do you know? It's 972 pi, okay? So it gives us a little shortcut for being able to find the volume at any given time instead of having to use 2 functions. I got this one. And the reason I got this one is guess what I did with these 2? I technically combined them by plugging one into the other one. So it made 2 become 1, a much easier to use function. Okay, so let me erase all that junk because I want to make sure I don't confuse people when they look at that. Okay, so here we are. We're looking at V compose R of 2. So we just have to take the 2. And remember, this function over here is V compose R of T, right? That's what it is. So we can just straight up plug 2 into it. I'm going to take 2. We're going to put it in right there. Let's see what we get, you guys. So V compose R of 2 would be 36 pi times 2 cubed. So 36 pi times 8, that's what 2 times 2 times 2 is. So let's see what 36 times 8 is. It's 288. Okay, and these would all be cubic units. I haven't been putting, what are we measuring with? Oh, inches. So this would be inches cubed, you guys. That would be our volume, right? That'd be our volume at time 2. It says to interpret it, right? Okay, this is the volume. 2 seconds. Okay. All right, so hopefully you, from this example, why do I include it? It gives us an idea about why we care about function composition. It just makes our life so much quicker, instead of having to, okay, find out first, well, when time is 2, what's my radius? Let me come up here and use this equation. Now that I finally have my radius, now I can plug it in. Now it makes it to where we can take the 2, directly plug it into a formula and get our volume out. Okay. All right, you guys, that is it for 2.8. Take care.